Hello, we are Group 5 and this is our Plan D RoboCart. So, the problem traditional lawnmowers. While they have been a stable tool for keeping our lawns tidy, they bring along a set of challenges that can greatly affect their usability. One significant challenge is the physical strain associated with the mowers. The repetitive motion and the weight of the mower can quickly lead to fatigue and discomfort. The physical strain is even more pronounced for individuals with limited mobility who may find it particularly challenging to exert the necessary force and energy. This can turn a simple chore into a tiring and potentially difficult task. Moreover, traditional lawnmowers also pose limited accessibility. Operating these mowers can be a challenge for specific demographics, such as the elderly or individuals with disabilities. The complexity of starting and controlling the mower can create barriers for these individuals. So, our solution is a robotic lawnmower that addresses the challenges associated with traditional lawnmowers while promoting ease of use, accessibility, and convenience. But for this solution to be real, we will solve the problem for specific garden conditions. And those conditions are the garden should be surrounded by a wall or object that has at least the height of the lidar sensor that we will explain later. The grass should not be too tall, above 7 centimeters before cutting it. The maximum area of the garden is 25 meters, quadratic meters, and it has to be able to connect to the internet within the area. The area was found by the calculus using the battery durations estimation, wheel circumference, and the motor RPM. The garden is for domestic purpose, so the land should not be too tall and not surpass a slope of 15 degrees. Obstacles on the garden should be the same height or higher than the lidar sensor, and there can be dynamic obstacles. Steps need to be the same height or higher than the lidar sensor. The robot will operate just under clear weather conditions, as even for traditional lawn mowing, it needs to be with clear weather conditions. And the grass should be one of the following types, as Gramazion zoysia and Grama geozoysia. And the main benefit of the solution is to keep the grass height at a pleasant level and be uniform along the time. So the project structure, as you can see, there we have the front view, down view, and side view. It will have four wheels. The cutting will be made by lawnmower wire. Upside the support will be a case for the electronic components to be protected. Upside there will be the lidar sensor. On the sides we will have handles for the person to grab the structure.
Here is a diagram that best illustrates how our project works. We can see that the user interacts with the robot through an app. This app communicates with the Raspberry through HTTP requests, so there needs to be an Wi-Fi signal. Through the app, the user checks the status of the robot's battery, programs a job for the robot, like cutting the grass or creating a new map, sees the map already created by the robot, and selects the cutting area. It also warns the user if the robot is stuck at any point. The app is responsible for starting every robot process. The LiDAR connected to the Raspberry is used for localization and mapping, and will have 5 motors, 4 of which are the reduction box motor. To move the robot, these motors have high torque to prevent the robot from not being able to walk due to its weight and the terrain. The other motor is a brushless motor. This motor is typically used for drones, and in our researches, we discovered that it's very good for mowing grass, as it has high torque and also a high RPM. We'll have two power sources. The first is a power bank that will power the Raspberry and the LiDAR. We chose that because it has the correct voltage and meets the higher consumption that has presents, guaranteeing a long duration. And the other source is a LiPo 2200 milliampere hour battery that will power the motors. This was chosen because it has a higher voltage and will be able, through our calculations, to keep the motors running for between 2 and 2.5 hours. We took into account that in the mapping phase, the cutting motor will be stationary and in the second phase it won't, presenting a variable rate of battery consumption, so this margin duration. We also took in account the data that each wheel motor consumes 170 milliamperes hour, and the main motor consumes approximately 250 milliamperes hour. And we also have a battery level indicator so that we can inform the user. Here's our budget. As you can see, we've gone a bit overboard because we're using the LiDAR sensor, which has a very high pre-components that are more expensive. The raspberry, the power bank, and the motor shield.
So now I will talk more about the robot navigation phases. So in general, the robot's navigation through the environment will have two phases. The first one with the objective of mapping the area containing the grass to be cut. Then, after completion of the mapping, the end of this first step will be indicated to the user through a notification in their application previously connected to the robot, with a guarantee that the robot knows the environment sufficiently to carry out its work. In addition, the user has the option of saving the mapping performed on their smartphone for future uses, without the need to perform the mapping of the environment again. In this way, the road must be manually positioned at the origin of its navigation, initial position of the first stage, and indicated by the user through the application, which can start the second stage. In this second step, we will have the robot navigate through the location that was mapped in order to trim the grass. After the first use of the robot, the appropriate map must be selected in the application before start the second phase. If there is none, a new mapping must be performed. Specifically speaking, robot navigation will be based on the node structure that Robot Operating System (ROS) provides. In short, a node for this structure is a code module capable of communicating with other nodes. This communication between the nodes is done by messages, called topics. Therefore, the node subscribed to the node that sent the message receive this message establishing the communication. Next, we have the initial basic structure imagined for the operation of the robot's navigation, considering the use of the ROS node structure. This image was obtained from the ROS website in order to demonstrate the possibility of application in the proposed robot. The first navigation phase consists of a SLAM, that is simultaneous localization and mapping, and will be linked to the map server node in the right, which makes use of the move base node package in the middle for movement and obstacle avoidance using global and local planners. Concurrent with the use of this node, we have the use of the node entitled AMCL in the left. In the image that uses the nodes, sensor transforms for transforming the data obtained by the sensors for real-time simulation of the ORS platform, odometry source, which by calculating the differential between the rotation speeds of motor pairs in each side of the robot allows identifying its position in the environment, and sensor sources that provide information about the point cloud generated by the LiDAR scanner. Immediately after completing the mapping activity and before notifying the user, the route will be calculated based on the obtained environment map, which takes into account the size of the environment and the cutting area supported by the robot for grass trimming. Bearing in mind that the environments established will be rectangular, or sets of rectangles, and in addition, with the aid of computer graphics and the data structure of the map of the environment that will be obtained, and together with the coordinates relative to the origin that was initially established by the user, it will be possible to establish points where the robot must travel to carry out the trimming in a suitable region of grass. Thanks for the attention.